Hello. You can see me, but for those on the video, hello, I'm David. I'm the coordinator of the Maths Learning Centre, and we're going to be talking about multivariable calculus today in Maths 1B. It's the summer semester in 2019. Hello from the past. Those who are watching in the future, I'm doing several revision seminars this summer because I wanted some stuff for you guys in the future, actually, and you who are here now as well, but also I'm doing several so that we can be ready for the new year. So, I'm talking about multivariable calculus in Maths 1B. Might as well put a title on here. What I'm going to try and do is I'm going to try and organise the way I think about all of this in the hope that since it makes sense to you, this is the way it makes sense to me, and I will make sure I talk about all the things that are in the multivariable calculus, but to get there I'm going to need to talk about some ways that I imagine things, and I've got various different physical things to show you to help you with your imagination. Because imagining how these things look is a useful way of understanding what's going on. So before we even get to the calculus, I'm going to need to talk about a few things first that will make sense of the things I'm going to say later. So the first thing I want to talk about, I'm going to talk about two things, and one is functions and one is equations. And the different ways of thinking about them that are used in order for multivariable calculus to do its job. So let me talk equations first. And in fact, what I'm really talking about is sets. So ever since Descartes, back in, I don't know when it was, several hundred years ago, we've been able to use numbers to label every point in a plane or every point in 3D. And so we'll have axes, which we're familiar with, and we'll maybe line it up with 5 here and 3 here, and that point will be 5, 3, like that. And we've been able to give a number label to every point in this plane. And it's called the Cartesian plane for that reason. And then we can do it in 3D as well. I tend to draw 3D like this. And then you line up something here, you go this way and then that way and then up, and you'll get a point like that. And maybe this point will be, I don't know, 2, 3, 4 or something. So we're used to doing that, and that's been done for several hundred years in mathematics now. Which is like the third purpose of number. The first purpose is to count, and the second purpose is to measure, and the third purpose is to locate. So we can locate things with numbers using these coordinates like this. And one of the things that Descartes wanted to do when he created this was to be able to describe drawings, like objects in 2D and 3D, using equations. So what he wanted to be able to do was to take a drawing and say, well, there must be a rule to tell whether a point should be on that drawing or not. And that's a set. And so that's one of the biggest ideas in mathematics, is that a set is, and I need to use another word that also means set, because otherwise I'd use set again. So they usually say collection. It's a collection of objects with a rule to tell if any object is in the set or not. And that bit just there that I said is the most important part of a set. There has to be a rule to decide if an object is in the set or not. And if we're using numbers, if our sets are made of points, and we're using numbers to tell us which point is which, then it would be reasonable for our rule to tell if an object is in a set or not to be based on those numbers. And so what we can do is we can say, hey, why don't we make a set where we do a calculation on the numbers, the coordinates of those of my point, and if that calculation comes out to a certain answer, it's in the set, and if it comes out to any other answer, it's not in the set. And so the classic example is this. The set of points with x coordinates x and y such that x, 3x minus 2y equals 7 or something. I don't want 7, I'm sorry, I'm going to choose 6 because that'll make my example a little easier. Okay, so what this is saying is that the rule for being in this set is that you take the x and y coordinates and you put them into this formula, and if it comes out to the answer 6, then it's part of the set, and if it comes out to any other answer other than 6, it's not part of the set. Okay? And from our experience with equations, we can know that this kind of equation always produces a straight line. But I'm going to be even more basic about it just to really ram my point home. So, what I'm going to do is I'm going to pick some points and see if they're in my set or not. So let's see. The point 0 is 0. 3 times 0 minus 2 times 0 is 0, which isn't 6, so this point is not in my set. So I'm going to colour it in blue. In fact, I won't use Play-Doh because I actually want to colour it in. I'm going to colour it in blue because it's not in my set, because my set's going to be yellow. And let's see, let's pick 1, 1. 3 times 1 minus 2 times 1 is 1, which is not 6, so this isn't in my set. Okay, and 2, so that's not 1, 1. That's 1, 1. Yeah. 1, 0, also not in the set. 2, 0, 3 times 2 minus 2 times 0 is 6. Okay, so this one is in my set. Lovely. And you could imagine going through all of the points in the entire of the plane, of which there are infinitely many, and colouring them in blue if they're not and yellow if they are, until you found all the points in the set. So I might go down the y-axis. 0 minus 1 is not in the set. 0 minus 2 would be 0 times minus 2 times plus minus 2 times minus 2, which is 4, which is not in the set. 0 minus 3, 3 times 0 minus 2 times minus 3 is in fact 6, so this one's in the set. And in fact we'll discover that as we start doing this, all of these points and all of these points, none of them are in the set, and we end up with these points in the set. And so we can find our set, it's a very poor way of finding a set, by colouring in all the points that satisfy the rule. So the thing is that every point out here produces a number when I do this formula that isn't 6. And only the ones on this line produce the number that is 6. Okay, now it's not a particularly good way of making a set. So what we've done over the last several hundred years is we have found out that certain kinds of equations always produce the same kinds of shapes. And we now know that an equation like this always makes a line. And we can, knowing that it makes a line, we can go, oh, well, what does x need to be if y is 0? Oh, x has to be 2. And what does y need to be if x is 0? Oh, y has to be minus 3. And so knowing it's a straight line, it has to go through those through points, and we can join it up. Okay, right. Every time you see an equation with various variables in it, and it doesn't even have to come out to a specific number. It can also have, x squared plus y squared equals 3x plus 4. It doesn't matter. It should be possible to figure out, to colour in all of the points that satisfy it, and they are the set. Cool. Okay. Nice. And that's important. So I want to do one more. And the other classic is this. It's in 3D this time. Something like that. And I could again run through all of the points in 3D and figure out which of them are part of that set and which of them aren't. And if I did that, and what I would discover is that all the yellow ones that I coloured in would all be on a plane. This is always a plane. Okay. So if I kept this bit the same and changed that number, I would get a different plane. So I collect together all the points where this calculation comes out to 30, then it's this plane. If I collect together all the points where it comes out to 20, it's a different plane, but it's a plane. And it's important to know that this is one of the ways of representing a plane. Okay, that's important. It's in 3D, I suppose. Okay, right. So the next thing I want to talk about, now that I've set that up, because it's so important, it never goes away, is that I can create functions. Okay. So you've seen functions. Functions have inputs and outputs. There are lots of ways to describe what a function really is mathematically. So what I'm going to have here is not a definition, but it's just an idea of what a function might be. So a function, well, it has a rule that using some inputs, well, using inputs produces an output. Now we might have some functions where we just have a list where we have a list of all the inputs and a list of all the outputs, and that's a function. But usually what we have is that the inputs are some sort of number, and the rule is a formula that you do a calculation on those numbers, and that calculation is the output. And you are used to thinking of functions in a certain way, and I need to give you a few other ways to imagine functions in order for multivariable calculus to make sense. At least this is the only way it can make sense to me. So I'm going to give you a few metaphors, a few ways of imagining functions that will be useful. So I'm going to deal with functions that have just a single number in and a single number out first, and then I'm going to think of it in another way as well. So firstly, this is the notation. F of x is 2x plus 1. You're used to that. And this is saying that when we take the input x, the output that's produced when we take the input x is 2x plus 1. So the first way of me imagining functions is this. I'm going to draw a number line for all of my x's. I don't always do this, but I'm just imagining. And then every one of those numbers produces an answer when I put it into the function. Okay, so when I put in the number 0, the answer is 2 times 0 plus 1, which is 1. I might change colours, I might use this colour, which is 1. And when I put in the number 1, the answer that comes out is 2 times 1 plus 1, which is 3. When I put in the number 2, I get 2 times 2 plus 1, which is 5. When I put in the number minus 1, I get 2 times minus 1 plus 1, minus 2 plus 1, which is negative 1. 2 times minus 2 plus 1 would be minus 4, which is negative 3. And I could also put in any other number. Like I could put in a half as well. So here at a half, the answer is 2 times a half plus 1, which is 2. And here at minus a half, 2 times minus a half would be minus 1 plus 1, which is 0. And every point here has a number attached to it that it produces when you do the function. And that is a way to imagine it. I'm going to get you something that you know does a similar thing if you've seen it before. You may or may not have seen this sort of thing before. It's an advent calendar. Okay? And in an advent calendar, it's lovely, this Christmas countdown calendar, they're all lovely kittens. In an advent calendar, every number has a little window, and behind the window is, well, there was chocolate. Once upon a time, has a little piece of chocolate in a little Christmassy shape. So every number has something that it produces when I open the window. That's how I think of a function. That here, there's a little window here at 0, and I open the little window, and behind it, it has the number 1. That's the function value. The reason I think of it this way is it's not like you have to wait to calculate this for the function value to be there. It's already there. You calculating it is just opening the window to reveal the number that is already there. Every number on the x-axis has a number attached to it already, whether you calculate it or not. That's an important way to think about functions. and the advent calendar is my metaphor for that. Okay, I needed to bring a real one for, it was important to me. Okay, so I can imagine, as I move back and forth along here, I can imagine what happens to the number as I move. And it's hard to imagine that because the only thing that's a geometry space thing is this line here. And the numbers at the moment aren't geometry in space. But that's okay, I'm going to move on to that. But I just wanted to let you know that this is what's going on. So I can imagine looking in the window and seeing that number change and saying, how does the number change when I move back and forth here? That's important. I should say, and the other way of thinking about this is as temperature, or each number is a temperature. So this line has a temperature, and as I move along it, I will change temperature, and over here it's sort of warmer, and over here it's sort of colder, and that sort of thing. So they're good metaphors to be using, and I will come back to them as I go along. Right, so the next picture of a function I have is only a little different to that. So I'm just going to write advent calendar here. And I'm going to leave a space, and I'll put a picture of it here when I... No, I won't. Advent calendar is my metaphor for this. Okay, so my next picture is this. So here are my X things here. And what I'm going to do is I'm going to imagine having my window open and seeing that number change as I move along. So as I move along here, the number that's here changes as I move back and forth. That's my advent calendar picture. But instead of having the written number there, I'm going to draw another number line. So I can imagine here that if I walk this way, so here, let me just put a 0 in here. Here at -1, the answer was -1. And as I walk here, it goes up to there, and then it goes up to there, and then it goes up to there. And I can imagine as this moves along, this moves up and down. This one doesn't have to be vertical, it could be horizontal as well, it doesn't really matter. But what I can imagine is that as I move this way, oh no, crap, that's the wrong answer, but that's okay. Then the answer will move this way. And if I move this way, this answer moves that way. So I can coordinate these two different movements and think, well, what does moving here, what does it do to this? So that's my second picture of function. And this is a little easier to think about what happens when I move the x, and I can go, oh, okay, the y is going up. Well, I start calling it a y in a minute. This is going up or down. The output's going up or down when this is going forwards or backwards. And so some functions, well, let's think about what a function like this. All right, so if I start moving this way, so if I start here and go that way, then 0 squared is 0, and 1 squared is 1, and 2 squared is 4, and 3 squared is 9. And so this starts to get faster and faster. The further along here, the faster this is. And if I go this way, it goes up as well. So I can imagine starting at 0 and going one way or the other. So if I went this way, this goes that way. And if I go this way, that goes that way as well. And if I was over this side and I went this way, it would go down. And if I was on this side and I went this way, it would go up. And that would be various different things. And so I can actually see that 0 is the minimum, because when I'm at that spot, no matter which direction I go, I'm always going up from there. Okay. So that's the second image of function. I used to have a Desmos that did that, but I forgot to set it up. Give me a minute. Okay, so this is the picture of f of x equals x squared, and this blue line here is my this blue line here is my x-axis, this purple line here is my y-axis. and as I move this back and forth, that green point moves. So here I am over the negative, comes down, then starts going back up again. And the further away from here I am, the faster it goes. Okay, that's my second picture of function. Okay, and my third picture of function is the one that you're familiar with. So the third picture of function is the one you're familiar with, where you take these numbers that are attached to each one and you interpret them as heights and depths. So you go, here's my x-axis, and I go, well, the number attached to here is 1, and so I'll go up 1 and I'll draw a dot there. And then a number attached to this, so this is f of x equals 2x plus 1 again. The number attached to this one is 3, and so I'll go up 3 and I'll put a dot there. And the number attached to this one is 0. Sorry, not 0. The number attached to this one is -1, so I'll go down 1 and I'll put a dot there. And I can join all those dots together and figure out for every x coordinate what the height or depth I should go and draw a dot at that point. And so what I actually imagine is an x and a y plane. Whoa. Do you know what? I actually brought a ruler. I did quite well, actually. And I can colour them all in. And that action of colouring them all in was very similar to the action of colouring in all my points over when I had sets. And that's not a coincidence. So this is my third picture, and this is called the graph. If you want to look up what this one's called, some people call this the dynograph because it's dynamic. But you don't need to actually know what that's called, it's just an imagining. And so there are three different ways of thinking about function which are all useful for trying to understand how calculus works. Okay, so this one's not really geometrical at all. This one's sort of half, and this one's full-on geometry. And the graph here is where it connects to sets. So what I could do here is I can imagine a set which goes, okay, the formula that I want to do is I want to say that the function value acted upon the x-coordinate has to match whatever the y-coordinate is. And that's the graph. So this would have been, you know, as an equation, would be that. So this equation can be interpreted in two different ways. I can interpret it as just a straight up set, you know, satisfy y equals 2x plus 1, then you're in the graph. And don't satisfy, i.e. that's not equal to 2x plus 1, then you're not in the graph. I can interpret it that way, or I can interpret it this way as the result of a function. You know, take every x and find, find the matching y. And make x, y, and draw it, and that makes my graph, my set in the other way. So not all sets are written this way. The first set that we had isn't written in such a way that I can interpret it as a function at the moment. It's not something where it goes, oh, well, I'll just take every x and figure out the matching y, and that will give me the point that I want. I mean, it could do it, it would just be harder work. Whereas this one's written both ways. So I can see this both as an equation and as telling me how to calculate a function at the same time. Right. But I do want to point out something very important, is once I've thought of it as an equation, then I can think of this same line in a different way. I could think of it as y minus 2x minus 1 equals 0, and at the moment that is not function setup, but it's still an equation and it's still the same line. So I could make a line in multiple different ways. One of them is as a function, and there are like a billion of them that are not functions and are just equations that happen to work out for every point on the line. Okay, they're the functions you're familiar with. Now I want to talk about functions of other numbers of variables. So functions don't have to use numbers. You don't have to take numbers in and spit numbers out. You can take in a point and spit a number out. You can take in a point and spit a different point out. But in calculus we talk about things that, at least in Maths 1B, things that take in a point and spit something else out. So what about 2D functions? Now don't be confused. You might have thought that this was two-dimensional. It's not really. I mean, this function here is not two-dimensional. It has one x, and that's the only thing that tells me where I am. So it's like a one-dimensional function. I can draw it in 2 dimensions by thinking that the output is the second dimension. Whereas when I say 2D functions, I mean that there's going to be 2 dimensions going in and an output coming out. So functions that go like from R2 to R, where I take a point in and it spits out, I don't know, something. Something like that. So what that does is that every point produces a number. So let's just see. Here's x, here's y, and this y is not the output from a function, it's an input for a function. These are both inputs. Whereas the last graph I drew, the y was the output and the x was the input. So I could, using this function, do exactly what I did with the advent calendar and figure out what every point has as its output number. And so here at 0, I get 3 times 0 times 0 minus 0 squared, which is 0. And here at 1, 0, I will get 3 times 1 times 0 minus, so that'll be 0. And these are all 0 along here. And then here at 0, 1, I'll get 3 times 0 times 1, which is 0 minus 1 squared, so that's negative 1 there. And that's negative 1 there as well. And here at 1, 1, I get 3 times 1 times 1, which is 3, minus 1, which is 1. So it's 2 here, and 3 times 1, so this is 1 minus 1. 3 times 1 times minus 1 is minus 3. So I get minus 4 here, and every point has a value that's attached to it. So this is my advent calendar picture of the function, that I can imagine that at every point I can figure out what value the function has. And I can imagine as I move through this picture here that the function value changes as I move. Now I have a bigger picture of this. Which everyone who's in the lecture theatre can see with their real eyes, but the rest of you who aren't here have to... right. So I have here an x-axis and a y-axis. I'm sorry some of the numbers are upside down, but you can still tell what they are because they've got dots on them. So I have an x-axis and a y-axis, and at every point, well, you know, these points anyway, there is a number attached to that. Now, I don't have a formula for this graph. I've just put the numbers in. So here at 0, 0, when I do f of 0, 0, I get 2, and when I get f of 1, 1, I get 3, and when I get f of 0, 1, I get 4, and f of 1, 0 is still 2, and all of those sorts of things. And so this is a picture of one of those 2D functions. Okay. Well, I'll come back to that in a second. Right, so the second view of a function is that second one I did, the dynograph. So you can imagine not just moving along here and feeling that the number is different because it's a temperature or something, or a happiness, I don't know. Maybe it's how the point feels, and these ones feel sadder than these ones. whatever. So maybe instead of trying to feel or see that the number is just by reading it, you could do the thing where you go a point moving around here, however it moves, would make this sort of, do something on the output. So here it's 0 is 0, and then as I go along here, nothing happens at all, it doesn't move. That's what happened here. And as I go along, go this axis, it goes down. Go this axis, down here, it also goes down. If I go this way, it goes up, and maybe it'll come down again, I don't know. So let me see if I can draw one of those as well on the computer screen. All right, so I've made my Desmos graph, and as I move this point around in the plane, the function value changes. So if I'm here at 0 and I move along there, it doesn't really move at all. If I move up, it goes down. If I move this way, it also goes down. If I move that way, it goes up. If I move down here, it goes up and then down again. So as I move all around here, the function value will go up and down. All right. I find that a very useful way of thinking about this. All right. But there is one last way of thinking about a graph, of thinking about a function that has two variables as its input, and that is to interpret it as a graph, or graph if you prefer. So I'm going to need a third direction to measure in. And before I do that, I'm going to actually do it on the real camera. Okay, so here at the origin it's 2, and here it's 2, and here it's 5. So at every point I can interpret the number that I have as a height. And I could do that not just at the grid points, but at every point. And then I would be able to see, without having to read the numbers, that the numbers are higher in some places than others. There we go. I won't do all of them, but I do want to do a few more just to make my point. Okay, so these things are higher. It's easier for the people in the screen to see it. That everything is interpreted as a height. And if this is so not going to work because they're all going to fall down. But I could join them all up and produce a surface if I join them all up. Instead of joining them all up and producing a line or a curve like I did with the 2D functions. Yeah, I broke it, but it's fine. I've wanted to do that for years. I'm so excited. Okay, now it's really hard to draw that on a piece of paper. And some people have different choices for how they arrange that. So some people will draw their x-axis this way and imagine that their y-axis falls backwards into the paper and so looks like that. And then imagine their output axis going up. And some people will actually imagine the x and y facing and the y coming out towards them. And some people will put the x-axis this way and the y-axis this way and the output axis that way. I prefer this one. This one makes more sense to me. Because I think of me standing just here, looking into the page, and I think of the page this way. and so that the up is up the page. But other people find this a little easier to interpret. I find this difficult to interpret because the positive x-axis comes towards me, so it feels like it's going backwards. The important thing to know is to make sure you have your x's and your y's round the right way, and you can use your right hand rule for that. If your thumb is the x and your fingers are the y, then the up should be coming out of your palm. So yeah, that works for that one, and that works for this one as well. And so what you do is that for every x and y, you draw a dot at the correct height or depth. So here they're all 0, and here this one's -1 and this one's -1. And here it's, oh God, it's 2, and it's really hard to draw, and eventually it will produce some sort of surfacey thing. Whatever. And this would be round a completely different way. So it's really hard to draw them on paper, and a computer can do a pretty good job. If you've got a computer that's designed to do 3D graphs, it can do a pretty good job. But again, some bits, we're not, it's two-dimensional drawing of a three-dimensional object, so it can be a bit confusing. But you can always make one if you want, just like I did on the floor. And I also like to use Play-Doh to make them as well, so to make a surface out of Play-Doh. And I do have another picture of one which can work on the camera. I'm going to come back to this, and I gave this to the lecturer this semester. This thing, if you look at it from this way, you can see that it has bumps and hills and valleys and things. I'll need to move my camera in a minute so we can look at it properly. But we can imagine this as a height above here, and each thing produces a height, and all those heights together make this surface. Okay, right. So now we have some imaginings for 2D functions. I have one more thing to say about imagining functions, and what if we were going to imagine 3D functions? Well, I'll do a nice simple one. What if we were trying to imagine a 3D function and we had f of x, y and z is this calculation? And so with that one, I'm not going to be able to imagine it as a graph the way I do with the 1D and the 2D functions. But I can imagine it in both of the other ways. So I can imagine that here in 3D, now the z is not an output, it's just one of the inputs. And this x, y, and z, at every point in space, there is a number behind the little advent calendar window that is calculated like this. So here at 0, 0, 0, the answer is 0. And here at 1, 0, 0, the answer is 1. And here at 0, 1, 0, the answer is also 1. And here at 1, 1, 0, the answer is 2. And here at 1, 1, 1, which is up here on the corner of the box, the answer is again 0, and every point in space has a number attached to it. And I can imagine it as my dynograph as well. So I can imagine as I move around here, then this function value will go up and down or whatever it does. And I would need to turn on GeoGebra to draw a picture of that, and I'm a bit rusty with my GeoGebra, so I won't do that. But you can imagine as you move around in 3D, the point will feel different. It's different temperature, or it's differently happy. The point will feel different, and that number is the output of the function. Or you can imagine as you move around in 3D, separately somewhere, there is something else that's going up and down. Right. And I know that took me quite some time to talk about, but it's really important to have these ways to imagine functions in order for calculus to make sense. Okay. And if you plan to study more multivariable calculus in the future, either in the course called Multivariable Calculus and Complex Calculus, or in the course called Engineering Maths 2B, then it's really important to have these pictures of function available to you. Okay. Right. So let's get back to what's going on in multivariable calculus. We're actually going to do some derivatives. Okay. So, derivatives are an idea about how quickly something, an output of a function moves when you move the input. Okay, so you have a function which takes things. I will put an x in bold to say it could be a vector if I wanted it to, and it produces an output. In fact, I'm just going to put the word input, if you don't mind. So f of an input equals an output. And so derivatives are a way of thinking about, you know, if the input moves, how does the output move? That's just awful, sorry. Bad writing. Too excited. And the answer to that question is what derivatives are for. Okay. So when we did derivatives, when we first learned them, we didn't learn them this way quite well, but this is what we were doing. So we imagined we had a function like, you know, f of x equals 2x plus 1, and we imagine as we move along the x-axis that we have a function value that's coming out, and we imagine that here we are at wherever we are, and if we move forward 1, this moves up 2. And every time you go forward 1, it goes up 2, no matter where you are. And so we decided that that meant that the derivative was 2. Okay. Just want to say something. So the things I've drawn here are what is referred to with those d's when you do a derivative. So I'm just going to actually call this y if you don't mind. This is a change in x. The d stands for difference. A difference in x. And this is a difference in y. And so with a straight line, the longer this is as well. If I move 1, then the change in y will be 2. If I change x by 2, the change in y will be 4. And so I'm thinking that the change in y is always 2 times the change in x. That's how a straight line works. And what we do when we do derivatives is we imagine that everything is straight if you look at it closely enough. Like everything behaves this way if we look at it closely enough. And so we go, well, dy on dx is in fact 2. But this seems dodgy to you, but you do it when you do substitution for integration. And it's a useful way of thinking about this for me. Right. With some functions, the speed at which you move is different depending on which x you're at. And so sometimes, you know, if I had y equals 2x squared plus 1, then I would have the thing that is here is different depending on which x I'm up to, because if I'm at a higher x, the y will move faster than it does at other x's. And so there's a formula that goes here, which in our case is 4x, that says that the speed at which y changes relative to the speed at which x changes is faster for bigger x's. The relative speed is faster for bigger x. Okay, and that's what we did. Only when you were first introduced to derivatives, you were introduced to them as the slopes of lines. And it turns out that it is the same thing. So in this second example, like that, you might imagine that here you are, and you went, well, if I move the x by a little bit, how much does the y have to move so that I stay on the curve? If I move along the curve, if I move the x by a little bit, how much does the y change? And that started to be a slope of a line. And the reason this works is because of this thing. So if I zoom in on a graph, so as I move this around, you can see what's going on nearby to that point. If I zoom in, so that I'm looking at a very small thing, it looks straight a lot of the time. If I zoom all the way in, it looks straight even at these curved bits here. And so if I'm looking very, very close, my function is more or less straight. And so I can pretend that it is nearby to that point. And that idea of functions are straight when you're close to them is exactly why we think about derivatives this way. That, well, document camera. It's exactly why we think about derivatives this way. So we're going to pretend that all things are like straight lines, and the change in y is going to be a multiple of the change in x, because that's how lines work. It's just it might be a different multiple if you're at different places. Okay, that was the derivatives of functions that you're familiar with. And that had all these cool rules like the chain rule and the product rule and blah, blah, blah. And there are different kinds of functions, and you learned how to differentiate polynomials, and you learned how to differentiate exponentials and logarithms, and you did a lot of stuff. And ultimately, they're all just figuring out how quickly an output changes when you change the input. But no one ever talked about why we always move forward. Wouldn't it be logical sometimes to think about, you know, I've got an input, maybe the input is the current temperature, and the output is the number of dust mites that are living in your carpet. And it might be that if the temperature decreases, the dust mites will die and there will be less of them. And we might sometimes want to make our x go down. So why do we never think about the dx going that way? It always bothered me. But we could if we wanted to. We could think, what would happen if the dx was negative? And the answer would be that if it was a straight line, if you went backwards, then this would just go down in the exact opposite way that it did when you went forwards. And that's why we don't really care, because it's always exactly the opposite. And it works that way even for functions that aren't lines, because if I'm really close to them, they look like lines. So I know that if the dx is backwards, then so will the dy, and it'll all work out in the end. Okay. That's just a thing that I wanted to point out. There's nothing stopping you doing a derivative in the opposite direction if you want to. It'll just come out to be the opposite change in y. Right. So what if we wanted to do this for functions that had two inputs? Ah, damn it. It's all right. There was another picture of two variable functions that I should have done, but we'll do it when we get up to it. What if I wanted to do this for 2D functions? Well, I could do it with my advent calendar, and I could move around my 2D function and imagine how quickly the output changes when I move, how quickly the temperature, the feeling changes as I move, or how good the chocolate is behind the advent calendar windows. Or I could think of it in the dynograph setting, which is probably the easiest one. And I can think, well, here I am, and I move a little bit in some direction, and that will cause my z to move in some direction. So this would be a change in z. And this thing here is both a change in x and a change in y. So this thing here is actually a vector made of a change in x and a change in y. All right. So the problem in 2D is that there is no forward. I'm standing here. In fact, I might just put the camera back on. Where is he? A little knight is standing there on the plane, and if he goes in different directions, the number will change in different ways. But it's not like there's a forward. I mean, generally, maybe where both of them are positive is sort of more forward than it is down here. It'd be more backwards. But which of these directions is more forward than the other? There is no forward. I can choose whichever direction I want. And so it doesn't really make sense anymore to only have derivatives going one way. And I should be allowed to do derivatives in whatever direction I want. And so I can imagine that when my little knight goes this way, so my dx dy is essentially the vector 1, 0, the function value didn't change. And so the dz was 0 if I go that way. Whereas if I go this way, the dz is 1. And if I go this way, the dz would be 2, because that's how much it changed by. But there's a problem with this. It's not about how much it changes, it's about how quickly it changes. So when I go this way, it goes up by 2, sure. When I go this way, it goes up by 2 as well, but my knight went further to get to that point. This distance here is longer than this distance. And so the fact that he went up 2 here means he actually, the number changed slower than it did here because it happened over a greater distance. Right, so somehow, if I want to talk about derivatives in 2D functions, I'm going to have to take that into account. I'm going to have to take into account how quickly the output changes and simultaneously take into account how fast the input was moving as well. And going in different directions along the grid points is going to be different. So, right. So I'm going to have to take that into account. And the way that I'm going to take it into account is to draw a new axis in the direction that I'm planning to face. So here we go. Now I'll make a surface out of Play-Doh. Right, this is my surface. It looks like that from the side. Ooh, that's pretty bad. That's not going to be differentiable there. Okay. Looks like that. It's pretty bumpy. From above, it's a bit hard to tell, which is important. I should have put an x and a y-axis on first, just a second. Okay. So, suppose that my little knight, so remember this is just a picture of the heights that represent those numbers. So my little knight can't see this, he's just standing here walking across and the numbers are changing. Or if you think about it, if my little knight was standing here, I'll make him a little yellow, this is my little knight. My little knight was standing here. From above, it just looks like he's moving left and right. And from above, you won't be able to tell if he's going up or down, if I'm looking directly from above. So I tried to move it directly under the, but it is directly under the camera. If he moves this way, you can't tell from the way you're looking at it whether he's going up or down. You can just tell if he's going left or right, and that's important. We're imagining this from a bird's eye view here, the direction that he's moving. Okay, so my little knight, I'm going to put him over here in the positive things. Whoa, there he is. And he's going to move in some direction. So let's suppose he moves that way. So if he moves that way, then this is the curve he is walking along when he goes that way. I could just as easily view it the opposite direction. That's the curve he's walking along when he goes that way. And so I can tell from this that when he goes that way, he's going to go down. And so the derivative in that direction is going to be minus, going to be a negative. But if I want to calculate what that derivative is, I'm going to have an axis along which to measure the distance that he moves. And so what I'm going to do is I'm just going to transfer him here. In fact, no, I'm not. I'm going to keep him where he was. Sorry. I'm going to put him down here. I'm just going to trace this curve. All right, there he is. I'm going to need to mark an axis along here in which to measure the changes in this direction, so that I don't have the problem of things being longer than they seemed, and so the change in the output is bigger or smaller than it seems. So in order to do the derivative, I'm going to need to measure this curve in terms of this distance, and that distance was along this line. So when the x moves this way, how far does the z, it's not really an x, when the distance moves this way, how far does the thingy move? And that's going to be my derivative. And I'm going to need to mark out an axis along that direction. And if I want to mark out an axis along a direction, I'm going to need a vector that is 1 unit long to figure out where the marks on the axis are. So this thing here I'm going to need a vector 1 unit long to do that. So, all right, this is not very helpful at the moment, because at the moment I have to have a Play-Doh drawing of it in order to do it. And I need to be able to do it with just calculation, so I don't have to pull out Play-Doh every time, as fun as that is. So I need somehow to find a calculus way of doing this. And I've already got a little bit here. I need to figure out a vector 1 unit long in the direction that I'm facing, so that I can figure out, measure distances in that direction accurately, mark out an axis in that direction. And I'm actually, technically, I suppose I'm going to need to figure out what the output is in terms of that movement along that direction, and then I could differentiate that. That'd be cool. Sounds hard. So I'm just going to restrict it to the easiest ones. Just for the later people who are reading it know what happened there. Insert Play-Doh here. Okay, so I'm going to just think about only moving in the x and y directions, because it's easier for me to figure out how far I've moved in that direction, because there's already an x-axis and a y-axis marked. So I can imagine that if I am here at this point, I could go, well, if I went this way, then how would this change? That's what I want to know. And this is just a dx. There is no change in y, the y stays the same. And so I can now think, all right, well, if the y doesn't change, now I can figure out exactly what the formula is doing. If I'm just changing the x's, I could just treat the y's as if they're a constant. And that's what I do. So now I'm saying, well, the dz will be something times dx. Only, but I've deliberately made sure that the change in y is 0. So it's not going to come into the formula. Okay? And this is called the partial derivative. So I go, the change in z is something times the change in x. And that thing is called dz on dx, curly d. Just to remind everybody that I'm keeping the other variable constant. So if I want to move the x by a little bit, then the dz will move by a bit as well, and it will be that times bigger than the dx. So if I moved x by 0.1, the dz will move by this times 0.1. If I move the x by 0.2, it would be this times 0.2. But the bigger that x got, the less accurate that would be, because it would stop being straight when you were far away. Okay, that's cool. And so what I do is I'm saying, all right, I'm ignoring the change of y. Y is constant. And I could just as easily do that in the y direction. And it turns out yeah, I can fit it on this page. So if I moved directly across diagonally, I could imagine that being made of a dx and a dy. And if everything was as flat as I think it is, so you know how when you zoom in on a curve, it becomes a line. If you zoom in on a surface, it feels flat. We live here on the Earth, which is curved, but it feels flat to us because we're so small relative to it. And so I can think, well, if it was curved, I'd be able to say that the change in the output will be a little multiple of dx. So the dx would cause the dz to move, the z to move, and the dy would also cause the dz to move. Like that. So basically, that is an awful arrow. The dx makes the z move a little bit, and the dy makes the z move another little bit. And together, that's the whole of dz. That's the idea. This thing here wasn't the entire of dz, it was just a piece of it, because I made the dy 0. And that is the big idea. And we're going to say this is how much the x moves. This is the curly dz on curly dy. X, and this is the curly dz on curly dy. And nothing up my sleeves. If I did a row vector times a column vector that looked like this, it would come out to the same answer. Is that not cool? Yeah. So if I want to do a directional derivative, I just need to arrange this dx dy to be pointing in the direction I want. And the way to do that, and to make sure that it is moving, that the axis along I move is marked out in units of 1, I need to put a unit vector in here to make sure it's in the right spot. All right, now that's a lot of talk. Now it's time to actually do the calculations. Because I've got 40 minutes left to fit in actual calculations. So they're all my imaginings about this, that I've now, thank you for indulging me, for letting me talk that out, but this is how I imagine these things. Even more, I imagine this as the change in the output is this thing times, well, this is a vector. It's a change in position as a vector. And so I can imagine this as dz is this thing times a vector change in x, which is kind of cool. Yeah. Okay. Right. So we're going to need to, if we want to calculate derivatives in whichever direction we want, which is what we need in 2D, we're going to need to know how to do those other derivatives, the curly dz on dx and the curly dz on dy. So okay, so partial derivatives. Okay. So when you do this, that means differentiate and x is the only thing counted as a variable, and dz on dy is similar. And so as an example, something like that, if I wanted to do dz on dx, then I would want to figure out the derivative of that, but treating everything except x as a constant. So let's have a look here. So when I look at this thing, it's got an x squared and it's got a y, but that y counts as a constant. So since the constant is multiplied on, it will still be there afterwards, because that's what happens with derivatives. If I had 5 times x squared, it would be 5 times 2x. If it was 7 times x squared, it would be 7 times 2x. And so that's one way of me making sure I've done it right, is pick a nice number like 7, which is not a nice number. Pick a number that you can tell where it is when you're finished for the y and see what you would do. So that would be this. So the 3 is multiplied on, so it will still be there. And then let's see, we have e to the xy. Well, the derivative of e to the anything is still e to the thing. But then the chain rule says I'm going to have to differentiate this, and the y counts as a constant, so the derivative of that will still be y, and the derivative of x is 1. Okay. So I get 2xy minus 3y exy. Well, let's try the dz on dy. So let's have a look at this. So this time the x counts as a constant. So I have x squared, that's still a constant because it doesn't have a y in it. So that'll still be there afterwards. And the derivative of y is, well, that's just 1. So if this x squared had actually been like 7, then it'd be like 49y, and the derivative would just be the number 49, which is what x squared is. Okay, that works. The 3 is a constant multiplied on, it'll still be there. E stays the way it is, and then I'll have to do the derivative of this. And if that x was like a 7, it would be 7y, and the derivative would be 7, which is the x. Yeah, so I treat the x as a constant, and constant times y differentiated is the constant. Cool, okay. And they are the two derivatives. Lovely. But that's great, but this is only telling me the derivative if I change the x forwards and I change the y forwards, what if I wanted to find the derivative in some other random direction? I'm going to do this now. I know it was way later in the course, but it makes most sense to me now. So what if I wanted to move in the direction of, say, 1, 1? No, 2, 3. Ooh. 2, 0. Okay, so what if I was at 2, 0 and I wanted to go in the direction of 1, 1? So technically you're not actually moving, it's not actually starting at, it's just at that point. All of my pictures, it's starting at that point and moving forwards, but technically it's actually, you're at that point and you're moving past it. So as I'm moving past the point 2, 0, looking from above, in the direction, 2, 0, in the direction of 1, 1, so with that, this is a vector 1, 1, not the point 1, 1. Okay, I would need somehow to combine this dx, dz, dy and dz, dx together, and I would need to do that. So what was my formula? Well, here it is here. Okay, so the dx dy is moving in the direction of 1, 1. I need a unit vector in that direction, and then I can dot it with the dz on dx, dz on dy. So let's go. What was the notation for this? Capital D and then a sub with the direction, and then the point, and then the f. Yeah. No, just the. So the notation for this is what is the directional derivative in the direction of 1, 1 of f at the point 2, 0. Is that how your lecturer wrote it? I know the grad is there. I'm going to have to look that up just a second. Has someone got their notes? You're the quickest. It used to be this notation, so I just want to check what it is now. Oh, yeah. There. D sub u f. Yep, that's what I want. So the D stands for the derivative. This vector stands for the direction. That f is the name of the function. And these 2, 0 is the point that I'm at. So the derivative in the direction of this vector at the point 2, 0 of the function f. Right. Okay. So I'm going to need to combine those other things together. All right. I'm going to need to figure out what these things are. At 2, 0, dz on dx is 2 times 2 times 0 minus 3 times 0 times e to the 2 times 0, which is 0. Sad, but anyway. And dz on dy is 2 squared minus 3 times 2 times e to 2 times 0, which is 4 minus 6, which is negative 2. Because e to the 0 is 1. Okay. Cool. And I need a unit vector in the direction of 1, 1. So the length of 1, 1 is the square root of 1 squared plus 1 squared, which is root 2. So my unit vector in that direction is 1 root 2 times 1, 1. And so the directional derivative in the direction of 1, 1 of f at 2, 0 will be dz on dx dz on dy dot with this vector. Technically that vector is written as a column. You know. Which is, what did dz on dx come to? 0 to negative 2, 1 on root 2, 1, 1. So the 1 on root 2 will still be there. 0, sorry, which is negative root 2. So this is telling me, just in my head I'm thinking, that in that direction the dz is minus root 2 times the dx. Basically. In a way it's sort of like du really. Yeah. Okay. So if I move in that direction, then if I move by 1 in that direction, it will go down root 2. Sweet. Okay. And that's all there is to partial derivatives really. You can do them multiple times. And so I'm going to switch track now and just do some of the things you've been asked to do. So let me switch track and summarise the things that I know of in this course. Because I want to get to tangent planes too. Okay, so the first things we had were the partial derivatives. Oh crap, just a second. Stop, I'm not going to do that. Right, making up crap here. So, here's the thing, when we do this directional derivative, when we try and figure out the derivative when we're facing a certain way, we need to know what both dz on dx and dz on dy are. And it turns out that the easiest way of arranging our calculation is to put them in a vector together. And we need a name for that vector. And that vector is called the gradient. So I should do that now. The gradient of your function is a vector that contains all the partial derivatives. So if, for example, if we had f of xy as the thing that I had before, which was then the gradient of f at the point xy is the vector which has the two gradients. Like that. So in our case it would be 2x minus 3y e the xy, x squared minus 3x e the xy. And that gradient is a vector that you calculate, and it will be a different vector at every point. So at every point in the plane, you will be able to calculate a gradient, and it will be a different vector. And at the moment, it's just a handy place to hold the partial derivatives. But it has, so that we can use it to calculate the directional derivative. So that's the gradient. And so that means that we can now say that the directional derivative in the directional derivative in the direction of u of f at the point xy is the gradient of f at the point xy dot with u, as long as u is a unit vector. So now we have a notation for this thing. Okay, sweet. So the gradient is a vector, it holds the partial derivatives. And the directional derivative is a number, When we dot this with a particular direction, you get a particular number. All right, so standing at some point, if you go in different directions, you will get different derivatives. And they will all be done by dotting your gradient vector at that point with a unit vector. But the gradient vector has some other magical properties. And to do that, I need to switch positions, switch viewpoints again. All right. Let me go back to this. So see this surface here? This surface was created by picking an x and a y, every possible combination of x and y, and figuring out for all of them what the function produced and interpreting those as heights and depths. But there is another way to make a surface. The other way to make a surface is the same as the other way to make a line. When I made a line, I could go along all the x's and figure out the matching y and create a point from that, and it would be the graph of a function. But I was also able to make the line by just picking an equation that all of the points satisfy and finding all the points that come out to the correct answer. I can do that with a surface as well. So a surface can also be created by picking a function in 3D of x, y, and z that produces the right answer when I pick a point on the surface. So I'm just going to need to go back to that. Whoop, surfaces via sets. So before, I could make a surface like, z equals x, y. And that's me imagining that there's a function x, y, of x and y that produces x, y as its answer. And then I go, I choose all the x, y's and do f of x, y as the height. That's one way of making this surface. The other way of making this surface is to say, well, it's the set of all x, y such that z minus xy is 0. Or xy minus z is 0. Or 2xy minus 2z is 0. Or x divided by y equals x, z divided by y equals x, or any number of other formulas. But the nice thing about this version is that this here, so this is a set, and we can notice that this thing here is a function of x, y, and z. Now I can create a surface without a function by doing this. I can go, oh, well, let's go x squared plus y squared minus zxy equals 5. And that would be a perfectly good surface that's extremely strange looking. But most of ours are going to be like this. But I can have a function of x, y, and z. And that would mean that there is some formula that I can calculate from all three of the coordinates that produces an answer. And my surface is all of the points that produce the answer 0. Just like when my line over here was all of the points that produce the answer 6, and different points produced answers other than 6, well, this surface would be all of the points that produce the answer 0 for this calculation, and all the other points produce an answer other than 0 for that calculation. So we have managed to create from our surface a 3D function. And my surface is just one piece of it. One piece of the 3D function, just the bit where it comes out to 0. So I'm going to need to just... still too low. So this might be where xy minus z, this is not xy minus z, but this might be where x minus z equals 0, and this might be where x minus y minus z is 7, and this might be where xy minus z is 8, and this might be where xy minus z is 4. Different answers for what we think it might come out to be will give me different surfaces. And the surface that I really want is just one of the surfaces I could have had. Right, so now that means that to analyse my surface, I can, even though my surface was the output from a 2D function, I can imagine my surface, analyse my surface by imagining it as one piece of a 3D function instead. So I could create a new function which I will call g of x, y and z, and I can go, well, g happens to be 0 on my surface. Okay, so how do I analyse 3D functions? That's a good question. When I analysed 2D functions, I noticed that there was a thing called a directional derivative. So if I move in 3D a certain distance, then that causes the output to move a certain way. And I can do a directional derivative in exactly the same way. I can go, well, this thing is made of a change in x and a change in y and a change in z. And so I could do my directional derivative in 3D in exactly the same way. I just can't think of it as a slope anymore because I haven't got a graph made out of, I can't have a fourth dimension to put my Play-Doh in when I make my graph. So I can think of it the same way though. I can do the directional derivative in the direction of u of f of x, y, z, and it would be d, what's this going to be called? What's a nice fourth letter? X, y, z, w. Yeah, right. dw on dx and dw on dy and dw on dz dot with u. And it's still the same as it was before. I just got 3 different directions to move in, and so I have to have 3 different partial derivatives, the same as it was before. So I can analyse 3D functions in the same way. And this thing here is still called the gradient of f. Oui. Only I'm going to change it to g because I don't want to get confused. I called my 3D function g on the previous page, so I'm just going to leave it with that. Okay. Right, so I can analyse it in exactly the same way, and I can think, well, if I move in 3D, how does the number change? But I can't imagine it the way I used to with the Play-Doh because, yeah, the dimensions don't work out nicely. I can only do it in this way of imagining it. Okay, so here's the thing. That gradient tells you how quickly you move in the x and the y and the z direction. But it's an actual vector as well. Right? It's got 3 coordinates. I could interpret that as a direction if I wanted to. What would happen if I interpreted it as a direction? And it turns out that if I interpret that as a direction, it's the direction you go to change the function value the fastest. Magic! So we had this idea that we have this vector that at the moment isn't really a vector, it's just a place to hold my partial derivatives. But I can, if I want to, imagine it as a vector, an actual direction. So back here, Where's the working that goes with this? My pages are out of order. Here it is. This vector 0, negative 2, that's the gradient vector at this point. At the point 0, 2, the gradient vector came out to be 0, negative 2. And at the moment, that's just a place to hold my partial derivatives. It tells me if as I'm going past this point in the x direction, the function value is not changing. If I'm going past in the y direction, the function value is changing at twice the speed as the y is changing. That's great. But this is a direction. I can go in the direction of 0, minus 2. I can go down the y-axis. What if I went in that direction? Well, then this unit vector would be in the direction of that. And it turns out that if you go in the direction that the gradient vector, if you interpret the gradient vector as a direction and you go in that direction, then the directional derivative is the biggest it can possibly be. So it turns out, let's just think about this. Interpret this as a direction. Okay, let's just say v is that direction. Okay, then the directional derivative in the direction of v of g at the point x, y, z is the biggest the derivative can be. Which is a magic trick, really. Okay, so what does that mean? What does that mean for my 3D, for my 2D surface thing? I had a surface. It was the output from a function of two variables, and then I went, oh wait, I could imagine it as just one possible piece of a 3D function, and that 3D function has its own gradient. What does that gradient mean? Well, that gradient means that it's the quickest way to change the function value. So, here we go. This is the magic trick. So I have a surface, and this is my surface. It's the surface I'm thinking of. And this surface is when my g comes out to 0. And then there are all these other surfaces that could have happened. This is where g is 1. This is where g is 3. This is where g is minus 1. And there are all these other surfaces that I could have chosen if I had wanted my g to come out to something different. So here I am. If I'm on this surface, g is 0. So if I move in a direction in 3D that keeps me on the surface, the function value doesn't change. And so the directional derivative of the g in any direction that's on that surface will be 0. Because if I'm on the surface, g doesn't change. If I go perpendicular to that surface, that will be changing g as fast as you can. Because if I go this way, out there, it'll take me ages to get to g equals 3. But if I go that way, I'll get to g equals 3 really quickly. And that is why the gradient of g points perpendicular to your surface. So what did we just discover? We just discovered that the gradient is able to do two things. If the surface is made as all the outputs from a function, then the gradient allows us to find the directional derivative. Like that. It allows us to find the directional derivative by dotting the gradient with the direction I'm going. That's one thing. if the surface is made as g of x, y, z comes out to a particular constant, usually 0, but nobody really cares, then the gradient of g is normal to the surface. That's what we have so far. And actually back here, it doesn't just find the directional derivative, it finds the direction in which the directional derivative is the maximum. Also, the direction of the maximum rate of change. Okay. Interesting. So there's one last thing that I haven't talked about, and I haven't done many examples at all, and if I have any more that you want to specifically ask about, I can do it on Tuesday. There's one last thing in this, or two last things that I haven't talked about. One is tangent planes. So I said at least some point in this last couple of hours that if you're on a curve and you're very close to the curve, it feels straight. And if you're on a surface like the Earth and you're very close to the surface, it feels flat. So if I have a surface, like my Play-Doh, and I have my little knight in shining armour sitting, nicely on the surface just here. To him, because he's so tiny, the surface feels flat. Now, not flat in a horizontal sense, just flat in a plane sense. To him, it feels like, just need some scissors. It feels like a little tiny plane when it's close to where he is. That's how it feels. And so we would like to know, what is that plane? That's the tangent plane. It's the plane that your surface feels like when you're very close to the surface. Which means that it has the same slope as my surface in every direction. So I need a plane that has the same slope as my surface in every direction, which means that this plane follows the surface. So something that's perpendicular to my surface is also perpendicular to my plane. And I have something that does that. That was the gradient vector. All right. Let me just go back to that. The gradient vector of, not the gradient vector of the surface considered as a function, the gradient vector of the surface considered as a piece of a 3D function. Also, this is normal to the tangent plane. Okay. So, let me do an example of doing that. Find the equation of the tangent plane to z equals, let's do the one that we had earlier. Now I'll just do a new one. Just do a simpler one. 3x plus 5yx. Let's just, yeah. Find the equation of the tangent plane to that. At the point where x equals 1, y equals minus 2. Okay. So let me just think about what this means. Here we are at the point 1 minus 2. And the function itself, it can be interpreted as a surface which is above or below here. All these numbers are interpreted as heights. Okay? And I want a surface which is, I want a plane which is looks like my surface when I'm very close to it. And so I need to imagine this as a set made by a 3D function, not as a surface made by a 2D function. So that's how I'm going to do it. So I'm going to define g of x, y, and z to be 3x plus 5yx minus z. Then the surface is actually g of x, y, z equals 0. That's what it is. It's made by that equation. So my surface is now all of the points in 3D space that when I sub in x, y, and z into that formula, it gives me the answer 0. And every other point in 3D space gives me a different answer. But if I find the gradient of this function, that will tell me how the direction to go to change that number here as fast as possible, which is guaranteed to be perpendicular to my surface. Normal to my surface, that's the proper word. So, a normal to my surface at any point x, y, z is the gradient of g. So let's see. dg on dx is 3 plus 5y, and that doesn't have an x. dg on dy is, that doesn't have any y's, 5x, that doesn't have any y's, and dg on dz is negative 1. Just note you can do this trick even if you don't start with a z equals. If you were just given a raw function like of three variables that was supposed to come out to 0, that had z squareds and other crap in it, you could still do this and it would still work. Okay, so that's the normal to the surface. So at 1, negative 2, the gradient of g would therefore be 3 plus 5 times negative 2, 5 times 1, negative 1. Okay, so 3 minus negative 7. Okay, so this vector is normal to my surface. If I go minus 7 in the x, 5 in the y, and up and down 1, that vector is normal to my surface at the point which is above 1 minus 2. The thing is that the real point on the surface is up here somewhere. It's not here, because I need to figure out the point that's actually on the surface. So, I have a plane which is perpendicular to this, and which passes through a point on my surface. Good. So, let's see. So the z-coordinate of this point is z equals 3 times 1 plus 5 times minus 2 times 1, which coincidentally is minus 7. So the 3D point is actually 1, negative 2, negative 7. That's the point I'm thinking of. Somewhere in space is a point 1, negative 2, negative 7. So 1, negative 2, down here. And the surface passes through this point, and when it's very close to this point, it looks like a plane. And the plane that it is perpendicular to minus 7, 5, minus 1. So minus 7 in the x, 5 in the y. This is the tangent plane. That's delta G. Like that. All right. That's a bad drawing, I'm sorry. But this is what's going on. It's like this, but it's more like down there. It's just under there, you see. Like that. Okay. So I have a plane. So the tangent plane is normal to delta G, which was negative 7, 5, negative 1, and passes through 1, negative 2, negative 7. So I just need to find a plane that's normal to that and passes through that point. There are multiple ways of doing that. So I'm pretty sure the lecturer did a thing with a dot product. I can never remember that. But I do know that the coefficients of the plane equation will be 1, negative 2, and negative 7. Not that one, sorry. Negative 7, 5, and negative 1. If it's normal to this, then the equation is going to be negative 7x plus 5y minus z equals something because of this from the normal. And I know that it passes through this point, so I can sub that in and it'll tell me what k is. So minus z, which is negative 7, equals k. So what do we get? Minus 7, minus 10, so negative 10. So therefore the equation is negative 7x plus 5y minus z equals negative 10. That's how I do it. I know that the normal produces the coefficients, and if I sub in the point, and then if I sub in this point, then it produces the correct constant. Your lecturer probably did this, so I just want to include that too. So, or you can do minus 7, 5, minus 1, which is the normal, dot with x minus 1, x plus y plus 2, z plus 7, equals 0. Which would have given me minus 7 times minus 1, which is 7x plus 7, 5 times this, minus 7. And so they cancel, and I get minus 7x plus 5y minus z equals negative 10, just the same way. Okay. Okay, so that is how to find a tangent plane. And the point of the tangent plane is that that's how the surface feels to someone who lives on the surface at this point. It's that thing. And it only really applies very close to the point you're at. Okay. So I'll crop 6 minutes. I will mention this now. So there is one last thing you might want to do, and that would be to find. No, I'm not. It's not going to. Yeah, I'm going to mention it now, but then I'm going to do it on Tuesday. So there's one last thing you might want to do, and that would be to find out where the maximums and minimums are of your function. So that's something we used to do in old calculus. We used to go, here's a function, where is it the highest and where is it the lowest? And we want to do it without having to draw it. And we used to do that. We could use the derivative, and the derivative was 0 at the place where your function was highest. And then you would do a second derivative, which could tell you whether it's curving upwards or curving downwards at that point. And so we could do that in 3D or 2D calculus as well. And in your course, you only do it in 2D calculus. If your function has the highest value it possibly can, then as you move past that point, you're not going to change very much, because you'll stop going up and start in every possible direction here at the highest point. You'll stop going up and start going down at every direction, no matter which way you go. You'll be going up as you go towards and down as you go away, every direction. So what you need is that in all the directional derivatives have to be 0 at the maximum. And because you make the directional derivatives from the gradient, that means the gradient has to be 0 as well. So when you're maximizing, you need all the directional derivatives to be 0. At a maximum or a minimum. There are other places where all the directional derivatives are 0 as well, so it doesn't guarantee it, and that means that the gradient at a maximum or a minimum. Now that's true in 3D, with 3D functions or 2D functions or 1D functions, and so if you want to find where the maximum is, then you need to find the gradient and figure out all the combinations of x and y where it's 0. But I will have to do that on a different day, because I only have about a minute to go and I can't extend the recording. So thank you for bearing with me. You are my guinea pigs to try this out, so that maybe I can get it right next semester. If you want to talk about it, about any of this stuff, Maths Learning Centre is open all the way until your exam in the afternoons, except on Wednesday, but your exams, no, there is a Wednesday. Okay, all afternoons all the way to your exam, and you can come and have a chat to us about it, and all of the Play-Doh and everything will be in the Maths Learning Centre if you want to play with it. Feel free to email me any questions you have about this that you want me to talk about later as well. Thank you.